Hello everyone, welcome to a new lecture of our Processing in Memory course. Today we are going to talk about how to program processing in memory architectures, and in particular how to program general purpose processing in memory architecture, the ABMEM PIM architecture that we presented in previous lectures. Remember that the system organization consists of a host CPU that is connected to some DRAM DIMMs that behave as the main memory of the system, and some PIM-enabled memory, some PIM-enabled DIMMs from ABMEM. Each of these DIMMs contains 8 or 16 chips, and inside each PIM chip, there are 8 DRAM banks. Connected to each of the DRAM banks, we have a DRAM processing unit or DPU. Remember as well that internally inside each PIM chip, there is a DDR4 interface for the host to access the data in the DRAM banks. And there is also a control and status interface for the host to communicate with the pipeline of the DPU. In the current generation of ABMEM-based PIM systems, we have 8 DRAM banks per chips. The size of these DRAM banks called NRAM is 64 megabytes. And in order for the pipeline to access this DRAM bank, there is a DMA engine. This way we can move instructions from the DRAM to the instruction memory and operands between the DRAM and the scratchpad or WRAM. And here you can see the pipeline with 14 pipeline stages. In the current generation of this architecture, this is an in-order pipeline that can run at a frequency of up to 425 megahertz, and it's a fine-grained multi-threaded pipeline with 24 hardware threads. Remember as well that there are 14 pipeline stages in this pipeline. In this pipeline, we execute instructions from the instruction set architecture, the ABMEM instruction set architecture that is a specific 32-bit ISA. Remember as well that it's possible to compile 64-bit C code. If you want to refresh about the architecture of the ABMEM PIM system, the DPUs, and also some micro benchmarking that we did of this PIM system, remember that you can take a look at these 2 lectures, lectures 2 and 3, delivered in this edition of the course. So let's start talking about how to program this processing in memory system. Remember that here in the ABMEM-based PIM system, we follow the accelerator model, where ABMEM DIMMs coexist with conventional DIMMs. And the integration of the ABMEM DIMMs into the system is seen as a loosely coupled accelerator. That means that we have to explicitly move data between the main processor, the host processor, and the accelerator that are the ABMEM DIMMs. And we also have to explicitly launch a kernel onto the ABMEM processors, the DPUs, and finally return the results to the main memory of the CPU. And this resembles GPU computing, as we discussed in the corresponding lecture. And if we have a system with a host processor or a system on a chip behaving as or acting as the host processor, and we have this PIM-enabled memory, the first thing, if we want to run code in this PIM accelerator, the first thing that the host CPU will have to do is to move data to the NRAM banks. After that, the host processor will transmit DRAM processing command to the DPUs, and then the execution of the DPU kernel can start on the DRAM processors, on the DPU. In the meantime, the host processor can continuously check if the data has already been processed on the memory side, and at that point, when the kernel finishes on the memory side, the memory banks, the NRAM, becomes again accessible to the host processor. We started to talk about ABMEM PIM programming a few lectures ago. When we started to talk about our first programming example, vector addition. Remember that in vector addition, what we do is the element-wise addition of 2 vectors, A and B, and we obtain an output vector C. In the ABMEM-based PIM system, the way that we are going to distribute the computation of this vector addition is by partitioning the input and the output arrays across the DPUs, the available DPUs, so in equally sized chunks typically, and then inside each DPU, we will distribute the computation among the available software threads that are called tasklets. The key reference to programming the admin-based PIM system is the SDK documentation, where you can find the user manual or a programming guide with many details and everything, all the different library calls and APIs that we are going to cover in today's lecture. From this user manual and also from additional presentations and white papers, we extracted a series, or in particular 4 general programming recommendations. The first one, execute on the DPU's portions of parallel code that are as long as possible. This makes sense because in the end, what we want to maximize or accelerate is the performance of our workload. And if this workload is massively parallel, we can benefit more from the parallel hardware that the DPUs provide. The second general programming recommendation is to split the workload into independent data blocks which the DPUs operate on independently. This is going to be important because, as we will see today, communication across DPUs, between DPUs is quite costly. So if we can partition the workload in a way that each DPU gets assigned independent data blocks and they don't need to access data in other DPUs, the performance of our program will be much higher. The next recommendation is to use as many working DPUs in the system as possible. Remember that in a real admin-based processing in memory system, we can have up to 2,560 DPUs. So we have many DPUs, and if we want to maximize the performance of our program, it makes sense to use as many DPUs as possible. And finally, the fourth recommendation is to launch at least 11 tasklets per DPU. This is something, this recommendation is based on the characteristics of the DPU pipeline, and we indeed double check this general programming recommendation with our micro-benchmarking experiments. We observed that the compute throughput of the pipeline saturates at 11 tasklets. So when we start the execution of a program that is going to make use of the PIM accelerator of the DPUs on the PIM-enabled DIMMs, the first thing that we have to do in our program is to allocate DPUs. Remember that we have more than 2,500 DPUs in the system, so we have to allocate DPUs in order to choose those DPUs or the number of DPUs that we want to use in our program. This is something that we are going to do with a library called DPUalloc that creates a DPU set, which is the set of DPUs that we are going to use in our program. And here you can see the syntax of this DPUalloc. Here we indicate what's the number of DPUs that we want to use, and this is the generated identifier of the DPU set. One question here is, can we allocate different DPU sets over the course of a program? Yes, we can, and we are going to show you an example next. But if we allocate multiple DPU sets over the course of a program, we may also want to deallocate them, and that's something that we do using DPU-free. But let's see this example. The example is Needleman-Wunsch. In Needleman-Wunsch, we have to change the number of DPUs in the DPU set as the computation progresses. Why is that? Because in Needleman-Wunsch, we are generating a two-dimensional matrix, and the way we generate this two-dimensional matrix is going diagonal by diagonal or anti-diagonal by anti-diagonal. And the size of the diagonals changes as we make progress in the computation. So based on the size of the diagonal, we want to allocate more or less DPUs in our DPU set. So that's why in every iteration of the algorithm, when we start to compute each of the anti-diagonals of the two-dimensional matrix, we first deallocate or free the previously allocated DPU set, and then we allocate a new set of DPUs depending on how many DPUs we need to use in the next iteration. So after having allocated the DPU set, we have to load the DPU binary into the instruction RAM that each DPU contains. And we use a library called DPU load to load a program in all DPUs of a DPU set. So here you can see this is the file where we have our binary, and this is the DPU load operation that we do to allocate this DPU binary into the instruction RAM of the DPUs in this DPU set. One question here is it possible to launch different kernels onto different DPUs? And yes, it's possible. And this can be useful, for example, to enable workloads with task level parallelism, or even different programs using different DPU sets. So essentially, we would need to allocate, maybe if we want to have task level parallelism inside a single program, we can allocate 2 different sets or more, and then load different programs in these 2 different DPU programs or DPU kernels in these 2 different DPU sets. Okay, so after having allocated the DPU set, having loaded the program into the IRAM, now we have to move the input data from the main memory of the host processor to the PIM-enabled memory. And also, after terminating the execution on the memory side, on the DPUs, we'll have to move the results from the MRAM banks, from the DPUs, to the host main memory. So, and that's what we are going to do using CPU, DPU, and DPU, CPU transfers. A CPU, DPU transfer is a data copy between main memory and the PIM-enabled memory. A DPU, CPU transfer is the copy of results from the PIM-enabled memory to the main memory. And as we are going to see, there are different types of transfers. It's possible to do serial CPU, DPU, or DPU, CPU transfers, where we are targeting a single DPU, just a single NRAM bank. There are parallel CPU, DPU, and DPU, CPU transfers. In this case, we target multiple DPUs or multiple NRAM banks at the same time. And there are broadcast CPU, DPU transfers. In this case, we target multiple DPUs, but we are going to transfer a single buffer to all DPUs. Let's start talking about the serial transfers. There are 2 library calls, CPUCPU and CPUCPU. The first one to copy data to the DPUs, to the MRAM banks. The second one to retrieve results from the DPUs. And this is how the syntax of these serial transfers look. And in this particular case is for CPUCPU. We transfer a buffer from to or from each DPU in the DPU set. And the first thing we have to use when we make use of this CPUCPU or CPUCPU is to indicate what's the area or the memory area of the NRAM that we are going to access. And to do so, we use this DPU NRAM heap pointer name that identifies the start of the NRAM range that can be freely accessed by applications. Observe that we don't need to allocate NRAM explicitly. Also observe here in the syntax that we have to indicate what's the offset within MRAM, starting from this MRAM heap pointer. The pointer to the buffers in main memory that we are going to transfer from main memory to the PIM-enabled memory, and the size of these transfers. So this is for the serial transfers. Remember that in the serial transfers, we are targeting a single DPU every time, as you see here. In the parallel transfers, we push different buffers to or from a DPU set in one transfer. All buffers need to be of the same size. This is a limitation of the current implementation of the parallel transfers. And to perform parallel transfers, we first need to prepare the transfer and then push them. And then in the when preparing the transfers, we have to indicate as well if we want the transfer to the DPUs or from the DPUs. And this is how we first prepare the transfer here, indicating what's the pointer to main memory. Then in the push library call, we indicate the direction. In this case is to the DPUs, the offset within NRAM, and the transfer size. And finally, we have the broadcast transfers. In this case, we can target multiple DPUs, but there is only the possibility of copying from CPU to DPU. So it's a new unidirectional operation, this DPU broadcast 2. We transfer the same buffer to all DPUs in the DPU set. That's why it's called a broadcast transfer. And this is how the syntax of this DPU broadcast 2 looks like. Notice that here we have the pointer to main memory and the transfer size. So one question that you may be asking yourself is it possible to use different types of transfers in a program? Yes, it's possible, and not only possible, but sometimes also necessary. For example, in this select operator, a relational algebra operator, where we essentially, what we are doing is filtering values of an input array. In this particular example, we are removing even values. What we do in a similar way as we do in the vector addition workload that we started the lecture with, what we do is dividing the input array into equally sized chunks that can be transferred to different DPUs for computation. And because these buffers are of the same size, we can use parallel transfers. However, the output of the select operation will have different size depending on what are the values in the input array. And what that means is that the size of the output in each DPU might change from DPU to DPU. And that's the reason why we have to use serial transfers for this particular workload, for the retrieve operation, the copy from DPU to CPU of the output results. These CPU, DPU, and DPU, CPU transfers are also very important. It's also very important to understand how they work and how fast they can be, because we also need to use them for inter-DPU communication. The reason is that there is no direct communication channel between DPUs, and all inter-DPU communication takes place via the host CPU using CPU, DPU, and DPU, CPU transfers. These enable us to, or allow us to, create different communication patterns depending on the characteristic of our workloads. For example, we can have more say simpler workloads where we just need to merge partial results in the host processor to obtain the final result. In this case, we only need to use DPU CPU transfers for this inter-DPU communication. Imagine, for example, the case where we are creating a histogram in multiple DPUs at the same time, and after having computed local per DPU histograms, we send all these histograms, these subhistograms or local histograms, to the main memory, and then we have the CPU performing a final reduction and obtaining the final histogram. Another possibility is to use these inter-DPU communication over the host CPU to redistribute intermediate results for further computation. In this case, we need DPU to CPU transfers, perform probably some computation on the CPU side, and then return the intermediate results by using CPU DPU transfers. Typical examples are iterative algorithms like graph processing algorithms, where, for example, in a top-down approach, we generate some output frontier at the end of each iteration of the algorithm, and in each DPU we are creating only part of the frontier, so we have to send all these parts of the frontier to the CPU for the CPU to consolidate the frontier and then redistribute it to the DPUs for the next iteration of the algorithm. But now let's see how fast are these transfers, because we have been working on that. We created micro benchmarks to obtain the sustained bandwidth of all types of CPU, DPU, and DPU, CPU transfers. And in particular, we ran two different experiments. In the first one, we target a single DPU. We use variable CPU, DPU, and DPU, CPU transfer sizes from 8 bytes to 32 megabytes. In the second experiment, we target a whole rank with 64 DPUs, and in this case we transfer 32 megabytes from CPU to DPU and from DPU to CPU for a set of 1 to 64 MRAM banks. We also run some preliminary experiments with more than one rank, and what we observe is that in this case, it's possible to exploit channel-level parallelism. Remember that the admin DIMMs, the PIM-enabled DIMMs, are connected to the host processor using several memory controllers and several channels, and that's the channel-level parallelism that we can exploit when we target more than one rank in our data transfers. Of course, because the PIM-enabled DIMMs are connected through the memory channel to the host processor, the DDR4 bandwidth bounds the maximum transfer bandwidth that we will obtain. But the cost of these transfers should be amortized, and the way of doing it is by enabling enough computation on the DPU side so that we can amortize the cost of these data transfers. Okay, let's start with the first set of experiments. As I said before, we changed the data transfer size between 8 bytes and 32 megabytes. And here you can see the results: sustained CPU DPU bandwidth or DPU CPU bandwidth for different data transfer sizes from 8 bytes to 32 megabytes. These are the results for CPU DPU transfers. This is for DPU CPU transfers. And one key observation here is that larger CPU, DPU, and DPU, CPU transfers between the host main memory and the MRAM banks results in higher sustained bandwidth. We can also observe in the figure that at some point the bandwidth starts to saturate. In the second set of experiments, we target a whole rank. In this case, we measure the bandwidth, the sustained bandwidth for CPU, DPU transfers, serial, parallel, and broadcast, and DPU, CPU transfers, in this case, serial and parallel. We changed the number of DPUs between 1 and 64, and in this plot, you're going to see the sustained CPU, DPU, and DPU, CPU bandwidth for the different types of transfers when changing the number of DPUs from 1 to 64, all in the same rank. These are the results for serial transfers. Remember that in serial transfers, we target only a single DPU every time. So if we are issuing serial transfers to 64 DPUs, these transfers happen one after the other sequentially, and that's the reason why the bandwidth remains flat. However, we see that when we increase the number of DPUs in the parallel transfers, we increase the sustained bandwidth. So this sustained bandwidth of parallel CPU, DPU, and DPU, CPU transfers increases with the number of DPUs inside a rank. Another observation here is the sustained bandwidth of CPU, DPU transfers is higher than the sustained bandwidth of parallel DPU, CPU transfers. The reason is that they are implemented in different ways in the admin runtime library. You can find a few more details in the paper that we wrote about the admin PIM architecture. The key reason for this small difference in the sustained bandwidth is that the copy operation between CPU and DPU uses AVX write instructions that are asynchronous, while the copies from DPU to CPU use AVX read instructions, which are synchronous, and that's the reason why they cannot achieve the same amount of sustained bandwidth. Another observation as well for the broadcast transfers, observe that we can obtain more or higher sustained CPU, DPU bandwidth. The reason is that because in the broadcast transfers, we are transferring just a single buffer to all DPUs in the DPU set, it's possible to exploit higher temporal locality in the CPU cache hierarchy. And this, in the end, has a positive effect in the sustained bandwidth between the CPU main memory and the NRAM banks. Another thing to know and to take into account when using these data transfers is that the library performs a transposition internally when we call these data transfers. The reason for that is that DPUs need a different layout of the conventional horizontal layout that we normally have in DRAM DIMMs. As you may know, in DRAM DIMMs, we distribute the bits of a word across the available chips. For example, if we have 8 chips in one rank, we every 64-bit word is divided into pieces of 8 bits, and these 8 bits, these pieces of 8 bits are mapped to the different chips. This is normally done in this horizontal layout is normally useful in conventional DRAM because this allows us to maximize the bandwidth when we access memory, when we access the DRAM rank. However, in the ADMEM system, DPUs need to have access to entire 64-bit words. So we have to perform this transposition in each cache line before writing it to the DPU's MRAM, or when reading data from the MRAM and moving it to the CPU side, we have to perform this transposition internally in the and it's transparently handled from programmer's perspective in order to make sure that every DPU has access to 64 consecutive bits, 64-bit words. So if you want to experiment by yourself with the CPU, DPU, and DPU, CPU transfers, you can access micro benchmarks that we created for our measurements. So now we know how to allocate, how to allocate a DPU set, how to load the program onto the DPU's IRAM, how to do these transfers between the host main memory and the PIM-enabled memory. Now it's time to launch the DPU kernel, the program, the code that is going to run on the DPUs. To do so, we use this DPU launch that launches a kernel on a DPU set. And there are different ways, or there are 2 different ways of launching this kernel. The first one is synchronous. This means that the host code, the host application is going to be suspended until the DPU kernel finishes. And the second one is the asynchronous kernel launch, where the control returns to the application and the CPU can continue doing, the CPU threads can continue computing while waiting for the memory side to finish, to terminate the DPU kernel. The only thing, if we use asynchronous kernel launches, is that we will have to use either this DPU sync or this DPU status to check the kernel completion. Why this asynchronous execution can be useful? What does it enable? Some ideas that I would like to share. First of all, it enables us to have task level parallelism, because we could launch one kernel on a DPU set and then return the control to the CPU thread, and then the CPU thread launches a new kernel, a different kernel, onto a different DPU set. So this way enabling task level parallelism, or also to enable concurrent heterogeneous computation on the CPUs and the DPUs. They might be working on either different data instances of the same problem, or different tasks of the same program, but we can have CPU and DPUs computing and working at the same time. And one last question before we launch a kernel is how to pass parameters to the kernel. To do so, we can use serial and parallel transfers, and it's possible to pass the input parameters directly to the scratchpad memory of the DPUs, to the working RAM. This is useful for input parameters and also for some results. And here you see an example of how to declare in the DPU code, how to declare some input arguments and also some results. We have to use this host qualifier, because even though these are going to be allocated in WRAM, we need them to be accessible by the host. So for example, if we want to transfer, we want to copy the input parameters, we need to use we can use either serial transfers or parallel transfers, but we would need to use these DPU input arguments that identifies these input arguments that we have declared in the DPU code. Okay, let's go back to our programming example, the vector addition. Remember that we are going to partition the input arrays equally and the output array equally across the available DPUs, and then we are going to do a similar thing inside the DPU by assigning different chunks of the arrays to the available tasklets. Let's take a look at how the DPU kernel for this vector addition looks like. First of all, what we do is obtaining the tasklet ID for every single tasklet that runs on a DPU. It's possible to get one identifier, and we need to use this identifier to address memory and to access the NRAM in a proper way. This is the size of the vector tile that is processed by this specific DPU. Notice that this is one of the input arguments that we have passed to the kernel. We need to define what are the addresses in NRAM for the input arrays, in this case, arrays A and B. Remember this NRAM heap pointer, there is where array A starts, and some bytes later at the end of the array A, we find array B. We also need to allocate memory space in WRAM. We are using, there are 3 different ways of allocating WRAM. In particular, in this example, we are using memalloc, which is an incremental allocator. And here you can find the main compute loop. Observe that in this loop, there is a let's say base index for each tasklet to access. We have to check all the time that we don't go out of bounds, and also observe that after each iteration we increase the index by the number of tasklets times the block size that each tasklet operates on in each iteration of this for loop. So when, after doing some bound checking, the first thing to do is to load data from array A and from array B that reside in NRAM into the WRAM. And to do so, we use the NRAM WRAM DMA transfers that are these NRAM read, where we can identify the addresses in NRAM, the addresses in WRAM, in this case, cache A and cache B, and this is the size of the transfer. After that, we are going to call this function here, vector addition, that is going to operate on the data that has been moved to cache B and cache A. We will see this particular function in the next slide. And finally, after obtaining the result, we will transfer the result from the WRAM to the NRAM, in this case, using a WRAM NRAM DMA transfer that is this NRAM write. Observe as well that in this case, the output values, the output contents are in cache B because we are reusing this cache B to store also the result of the vector addition. And here you can see the code for the vector addition itself. This is executed by each individual tasklet after having loaded chunks of A and B into the WRAM. The tasklet will go over all the elements in these chunks A and B in WRAM and performing the element-wise addition. Okay, so a few considerations about tasklets. Tasklets are the software abstraction of a hardware thread, and each tasklet can have its own memory space in WRAM. You have seen how we can allocate the space in WRAM for each tasklet using, for example, this memalloc, this incremental allocator. But tasklets can also share data in WRAM by sharing pointers, and that's possible, and we are going to see one example next. But tasklets within the same DPU can also synchronize. So there are intra-DPU synchronization primitives, in particular mutual exclusion or mutexes that we can use to create critical sections, parts of the code where only a single tasklet can be in, and in order to avoid data races and ensure correct execution of the program. It's also possible to use handshakes, another type of synchronization primitive, and in particular, these are useful to communicate from one tasklet to another tasklet. The second tasklet will be waiting for the first tasklet to finish to notify the second tasklet. We can use barriers. Barriers are a way of synchronizing all the tasklets running on the same DPU. And what will happen is when one tasklet reaches to this barrier weight, will have to wait until all other tasklets reach to the same point, and after that they will resume the execution. And finally, we can use also semaphores in cases where we need to use, for example, a counter. This typically for producer-consumer patterns where we have, for example, more than one consumer. So one example of how to use these synchronization primitives we can find in parallel reduction. In parallel reduction, we are going to have the tasklets in a DPU working together on a parallel reduction, on obtaining one single value out of a whole array inside the tasklet, inside the DPU. So same as we do in vector addition, for example, we can partition the input array into multiple chunks, assign each of these chunks to each of the available DPUs, and then inside the DPUs, we can further distribute this chunk across the available tasklets. For example, in this example, we have 4 different tasklets. The way that we are going to proceed is that, first of all, because we have assigned one chunk of the input array to each tasklet can go over all the elements of its chunk and perform the reduction sequentially in order to obtain a local sum. So at the end of this part of the parallel reduction, we will have multiple local sums, one per tasklet, that we have to further reduce in order to obtain the final local sum per DPU. So if we take a look at the code, we have this for loop for the tasklets to go over the assigned the chunks in MRAM that the chunks of the input array in MRAM that have been assigned to each of them after performing some bound checking and loading a piece of data or this block of data, loading it from MRAM to WRAM. We perform the reduction and accumulate in this local count. And after being done with this for loop, every single tasklet has a local sum. What they do is write in this local sum into some memory location in WRAM. And this message array has been declared to be accessible by all the tasklets running on the DPU. So after that, we synchronize all tasklets using this barrier weight, and finally, we can have a single thread reducing the local sums that have been written in this message array. So what this tasklet 0 is going to do is going one by one over the local sums of each tasklet, accumulating them in this message 0. And at the end of this for loop, we write this message 0 to this output variable that can be read by and accessed by the host processor. So here you see the barrier synchronization, and here the sequential accumulation that the thread tasklet 0 in this case performs. But this last step could also be done in parallel by using a tree-based reduction. You can here see how very basic naive mapping of multiple threads, or in this case threads or multiple tasklets, to perform a tree-based reduction. What we could do is assigning to each of the active threads 2 elements. So we are in the very beginning, we have 1 active thread. Every 2 elements in the first iteration, these threads perform this addition and accumulate in some temporary variable. In the next iteration, half of the threads retire, and the active threads continue performing the local sums, and they continue until as many iterations as needed. Usually, if we have an input array of n elements, we will need log n iterations. So these tree-based vector reduction can also be implemented inside the DPU, and we can implement it in different ways. For example, we can implement it using barriers. We can have multiple tasklets performing the tree-based reduction. After every iteration, tasklets synchronize with a barrier, and half of the tasklets retire at the end of an iteration. So you see, after this barrier, after all tasklets have finished their local reduction and have local sum, we execute this code for the tree-based reduction based on the barrier. So you see that in every iteration we have some tasklets that are active, and the active tasklets accumulate or add their own local value that is here in this message array in WRAM, and add the corresponding value that was previously loaded, previously generated by another tasklet that is at a distance of offset. And after at the end of each iteration, we have this barrier synchronization to make sure that the remaining tasklets, the tasklets that will remain active in the next iteration, will already find the corresponding values or the necessary values in the message array. And one thing here is that in the next iteration, half of the threads retire because this offset is multiplied by 2, which makes that half of the threads retire. It's also possible to implement this tree-based reduction in different ways. We also implemented it using handshakes, and the code is available in our benchmark suite. And the 3 different versions, single tasklet, barrier-based, and handshake-based, are compared in our paper. So if you want to learn more about the parallel reduction, which is an extremely useful primitive for parallel programming, you can also watch this lecture about parallel reduction on GPU that we have actually covered this week in our course on heterogeneous systems. So this is more or less all about this introduction to programming the admin-based PIM systems. Remember that a key reference for programming the admin-based PIM system is a programming guide or user manual that you can find in the SDK documentation. And we ourselves have been working actively with this SDK and with this programming of the admin systems, and have created our own set of workloads that we call PRIM benchmarks. The goal of these PRIM benchmarks is to provide a common set of workloads that can be useful to evaluate the current PIM architecture, the current admin PIM architecture, to compare also software improvements and compilers, and also to compare future PIM architectures and hardware. When creating these PRIM benchmarks, we adhere to 2 key selection criteria. The first one is to select workloads from different application domains. The second one is to implement workloads that are memory bound on processor-centric systems, on CPUs or GPUs, because these memory bound workloads are, let's say, the suitable candidates for processing in memory systems, at least in principle. So in total, PRIM benchmark suite contains 14 different workloads and 16 different benchmarks, because for 2 of the workloads, we have 2 different versions. And in this slide, you can see the whole list of workloads that are currently included in the PRIM benchmark suite and their different application domains, from dense and sparse linear algebra, databases, data analytics, graph processing, neural networks, bioinformatics, image processing, and parallel primitives. As I said, it's not only the diversity of the workloads in terms of domains or application fields, is also that these workloads have been shown to be memory bound in processor-centric systems. In particular, you can see here the roofline model experiments that we perform using Intel Advisor on an Intel Xeon CPU. And as you see, all workloads, all 14 workloads fall in the memory bound area of the roofline. But PRIM benchmarks are also diverse in terms of memory access patterns. There you can find some workloads with sequential, strided, and random access patterns, type of computation pattern, operations, and data types that they use, and communication and synchronization patterns, either intra-DPU or inter-DPU. In particular, if we talk about the inter-DPU communication, we find some workloads that simply do this result merging that I mentioned before when I talk about the inter-DPU communication, like workload like select, unique, histogram, reduction only need to use DPU-CPU transfers to merge the final results. However, there are other workloads that need to use DPU, CPU, and CPU DPU transfers to redistribute intermediate results. Examples here are the BFS, one graph algorithm, MLP, a neural network, Needleman-Bunch, which is a bioinformatics algorithm, etc. All PRIM benchmarks, same as all the micro benchmarks that we generated as well, are publicly available, and you can find them in this repository. In upcoming lectures, we are going to continue talking about these PRIM benchmarks, and we are going to use them to understand even more the admin-based PIM systems, and also to characterize the workloads and see what are workload suitability characteristics. So what characteristics make a workload suitable for the admin PIM architecture? And we, in later lectures as well, continue talking about more real-world PIM architectures and also about processing using memory architectures. So this is all for today. Thank you very much for your attention. Don't hesitate to contact me if you want to clarify anything related to this lecture or the course in general. See you in the next lecture.